Hello everyone, this video is about a gripe I have with the Python programming language. I feel like async is often treated like a magic bullet that will effortlessly make every code asynchronous and thus faster and efficient. However, I think in Python the careless usage of async will actually make your code more synchronous and slower, and this video is an attempt at explaining why I think that and how to avoid this. Take a look at these two code examples, one Python and one JavaScript, and see if you can tell what the difference in behavior is. In both versions of the code we call an async function that simulates sending a message and receiving a response after 1 second. This mimics a common pattern of functions that do, for example, database queries, REST API calls, or RPC. Instead of awaiting the send-receive function immediately, the code stores its return value and does some other work before waiting for the response. Even though the JavaScript and Python code are nearly identical, the output is always different. A lot of large language models also seem to struggle to grasp this difference. Both versions start the same at output starting, then the send-receive function is called. In JavaScript, this results in the message being sent immediately. When the await in the send-receive function is reached, the control flow returns to the main function. In Python, however, the function body of the send-receive function is not executed. Calling it merely creates the coroutine object, so the control flow returns to the main function. Then both versions do some other work, which might be some number crunching or anything else that doesn't involve async. After that is finished, both versions await the return value of the earlier send-receive call. In JavaScript, this means that the control flow returns to the send-receive function where the response is awaited. When it is received, the control flow returns to the main function. In Python, only a coroutine object was created so far, so the await starts the coroutine, which sends the message and then waits for the response. After a second of waiting, the response is received and control flow also returns to the main function. So now both versions completed sending the message and doing the work and waiting for the response. The difference lies in the order of operations. As you can see, the second and third line in the outputs are swapped. The JavaScript version sends the message and then did the work, in contrast to the Python version, which did the work first and then sent the message, even though it could have been sent right away. And not only is the output different, the Python code also takes longer to execute than the JavaScript code because the message is sent after the work is completed, so it couldn't be processed in parallel, and the response will arrive later, which makes the Python code pretty much synchronous, because no concurrency happens. This is caused by a little quirk in Python that I think doesn't get enough attention, especially by library authors. To be fair, this behavior isn't a bug or a secret. When looking at the Python documentation for coroutines, it says, "Note that simply calling a coroutine will not schedule it to be executed." This small line has what I would consider big implications on what kind of code async coroutines can be used for. Normally, to get the most concurrency, one would start the asynchronous operation as early as possible and then wait it as late as possible, to give it the best chance of completing in the background without any waiting. But in Python, the coroutine is not executed when it is called, so the asynchronous operation isn't started, so no concurrency can happen between calling the coroutine and awaiting it. The Python documentation lists several mechanisms to actually run a coroutine. The first is async IO run, but that one is of no help to us because it only works for the top level entry point. The next one is awaiting the coroutine, but that is of no help to us either because we want our code to do something while waiting for the result of the coroutine. If we await it immediately, our function is stopped until the coroutine completes. The documentation example also shows that the second coroutine's waiting only starts after the first coroutine is finished waiting. So the only scenario in which there can be actual concurrency when awaiting the coroutine immediately is if there are other tasks which then get to execute during the await, like in a web server that handles other requests as well. But not every Python program is a web server, and even in a web server scenario there's only concurrency if there are other requests happening at the same time, and the async await is of no use in making the response to a single request faster. The remaining options are async IO create task and the task group create task. But the latter is just async IO create task with an integrated barrier, so I will skip task groups here and stick to the normal create task for brevity. In the documentation example, the coroutine calls are wrapped with async IO create task and then both awaited independently, and this does indeed cause the tasks to run concurrently. So let's try to integrate that into our example. It takes the code from before and wraps the send-receive function call with createTask and everything is solved. Sadly, that isn't the case. This adapted code will still not start sending the message until after the work is done and the return value is awaited, because createTask also does not start the coroutine, it only schedules it for later. To give it a chance of starting, we have to yield to the event loop like an await async IO sleep of 0. Only then is there a chance that the send-receive function is actually started before doing the work. But that totally depends on the internals of the event loop implementation. I don't think there are any guarantees for current or future behavior regarding this, so I really wouldn't like to depend on this never changing. Especially if you send messages in a loop, the order you send the messages isn't determined by your loop anymore, but the order in which the event loop decides to execute the tasks. The await async IO sleep also allows any other task to run, which might require logs or other synchronization primitives. If you have other long-running tasks already scheduled, the message will also only be sent after those are completed, which might take a while. Another option is to also wrap the work into its own coroutine and await both, like in the documentation example. Notice that both createTask calls are essential for the message to be sent before the work is started. If you remove the createTask for the send-receive call, the event loop doesn't know of the task, so cannot start it when awaiting the inner coroutine task. If you remove the createTask for the inner coroutine, it is started immediately and the event loop doesn't attempt to execute other tasks. Only if the inner coroutine task would yield to the event loop at some point would the message be sent. And of course, if you remove both, the code is synchronous as well. To avoid this, you could use the async IO gather function to await both coroutines at the same time. So the order of the arguments to the gather function is then very important. But I ask you, for all these solutions, is this really the Python code you would like to write? To me, there's nothing Pythonic about that, and also consider that you potentially have to do this weird dance at every place where you want to call an async function and do something else concurrently. And because of the contagious nature of asyncs, there are a lot of async functions out there that actually don't do anything when they are called. I very much prefer the original version of the code and would really prefer if asynchronous Python code could be written like JavaScript. And it is. I'm going to let you in on something that seems to be a well-guarded secret. Your function can return an awaitable or even a coroutine object without being async itself. You don't need a coroutine to call a coroutine, you only need a coroutine to await a coroutine. So the real fix here is to not define the send-receive function as async to begin with. We remove the async so a function isn't a coroutine anymore and move the waiting for the response into a different coroutine. Then that coroutine can be called and returned from the send-receive function, and the return value can be awaited just like a coroutine. In fact, the signature of the send-receive function didn't even change at all. It still returns a coroutine object like a coroutine would do. That way, the message can be sent immediately when the function is called, and because the first thing the wait for response coroutine does is waiting for something else to complete, it matters a lot less that the coroutine isn't started until it is awaited. Of course, this just moves the weird workaround into the send-receive function itself, but at least that way it is only at one place and not at every calling location. But you might say, but how can I send a message without a wait? I need to execute a coroutine to send a message in the first place. Yes, this is a library problem I'm talking about, because this is not a Python problem. The Python overlords actually thought about this and avoided the problem. Take a look at the Python documentation for the async IO streams. If you scroll down to the streamwriter write function, we see that they aren't defined as async, so you can use them in regular function to write to the socket immediately. Sadly, this fact doesn't seem to be well known by package authors. I looked at several packages for messaging, file I/O or databases, and most of them use async functions, so the write function is buried behind multiple layers of abstractions. I'm also, of course, well aware that it isn't always possible to write to a socket immediately because a protocol, for example, might not allow sending a message at the current time. But concurrency is all about being eager, so libraries, especially ones that want to be fast, should at least make an effort to attempt sending a message immediately, and only fall back to delaying the sending if it is really not possible or allowed at the moment. Luckily, the situation greatly improved in the most recent Python versions. If you go back to the Python documentation about coroutines and tasks, there's a new section since Python version 3.12 named Eager Task Factory. Setting this eager task factory changes the behavior of every create task call to eagerly start the coroutine instead of lazily invoking it once it is scheduled. So if we go back to our example and use create task to call the send receive function again and also set the task factory of the running loop to the eager task factory, it indeed fixes a problem and the message is sent before other work is started. As an alternative to setting the task factory in the main function, a custom loop factory can also be supplied to the async IO run function using the loop factory argument. There was a discussion in the Python discussion forum about making this the default behavior, but it fundamentally changes the behavior of Python code, so it was rejected for now. Instead, the create task functions got a new eager start argument in Python 3.14 that allows controlling if a task should be started eagerly or not. That way we don't need to change the task factory for the whole program and can individually select which tasks should be started eagerly. So to summarize, ironically, to get the most concurrency in Python, you should not define your functions as async. Async actually makes concurrency harder. So if you define a function as async and the first thing your function does isn't awaiting something, consider not making your function async in the first place, but instead put the waiting inside an inner coroutine so the synchronous part of your function can execute immediately. Another thing to think about if you define a coroutine is naming. In my opinion, coroutines should not be named with lowercase verbs. Instead, they should be named like a constructor for a task, so instead of just calling the coroutine sendReceive, it should be called sendReceiveTask with an uppercase letter to properly reflect that the coroutine does not do anything when it is called and makes the behavior visible at the calling side, so the coroutine doesn't look like a regular function call. If you're using Python 3.13, try experimenting with eager task factory, and if it introduces any problem for your code or brings a performance benefit. In Python 3.14, you can use create task with the eager start argument to selectively start asynchronous processes without awaiting them and without changing the behavior of your whole code base. I'm happy there's some improvement in this regard, but to me it doesn't feel like it addresses the real problem of lazy coroutines. It also puts the burden of deciding if a coroutine should be lazy or eager at the calling side. I think this is a decision that should be made at the declaration side of the function or be part of the library. So I hope this video can bring some attention to this Python quirk and the new eager task factory. I still think we should add some rules to Python lint tools so we get warnings if there's non-trivial work at the beginning of a coroutine or if a coroutine isn't named like a constructor. But I doubt that any libraries are going to be rewritten to accommodate my preferred coding style. But what do you think? Would these lint rules be excessive? Were you aware of that quirk? Do you agree that this quirk is a real problem, or do you think there's no real impact at all? Tell me in the comments. Thanks for watching.